All right, so we've looked at the Laplace transform and we've looked at the inverse Laplace transform. And now we're going to solve differential equations using the Laplace transform. Okay, we've done all the hard work. Now let's reap the benefits. First, we're going to see how the Laplace transform acts on a derivative. So suppose we have this function that's continuous and its derivative is piecewise continuous and both functions are of exponential order. Furthermore, suppose for the sake of argument that f prime has a single point of discontinuity. Of course, we could, prove this for any finite amount of points of discontinuity, but just to show you how it would work, we're just going to consider one, okay, and it would work similarly to have a finite amount of finite discontinuities. So let's look at the Laplace transform of the derivative. Here's the definition. We're going to integrate to t naught. Why? Because t naught is that single point of discontinuity. And again, if there were more, we would break it up into multiple integrals. Now, what are we going to do? Well, how do you transfer a derivative from the function to the function it's multiplied by? You do that by integration by parts. And again, we have a video in the Calc 2 series, so feel free to look at that. When you integrate by parts, you transfer the derivative from f to this. Okay, you pay the cost of a minus sign, which we don't see here because we have two, minus minus gives you a plus, and you have this guy here. Okay, so that's what you're doing with this one. Okay, and you also do an integration by parts on this one, and you get this. Okay, now. Assuming s is greater than a 0, the infinity bound will give you 0. Okay, and one might think, well, what if f is just so large? Well, that's why f is assumed to be of exponential order, because we know then that f, that we won't get that situation where, you're getting infinity times an infinity that goes to anything other than 0. Okay, because again, it's of exponential order. And you get a lower bound of that t naught. That lower bound of t naught ends up canceling with this guy, the upper bound of t naught here. Okay, and from just taking, moving the derivative from f to e to the minus st, that's where these s's are coming from, or negative s's, but with a minus there that turns into a plus. And so you get this expression here. Okay, combine these with s's. You could factor out the s there. This is the term that's going to infinity there, okay, because the t naught's canceled. This is 0, as we said, for s is greater than c because of the exponential order. And so yeah, we're assuming that it's of exponential order with c. So as long as s is greater than c here, not necessarily just of 0, but of greater than c, then you'll get this going to 0. And you get this minus f0 from that lower bound there. Okay, now we could combine these. We could add these from just properties of integrals. And so you get this, but what is that? That looks familiar. Well, it's the Laplace transform of lowercase f, which we're going to write as capital F. And so the Laplace transform of a derivative gives you minus f of that function at 0 with s times the Laplace transform of the function, not the derivative, but the function itself, okay? Now we could do this again for f double prime, right? So the second derivative. And we could do this iteratively, right? So you'll get applying it on, so the second derivative is just the derivative of the first derivative, right? So you end up with this expression. So instead of Laplace transform of f, we have the Laplace transform of f prime minus f prime 0 instead of that, okay, with that s there. And now we know this, we just finished computing it, and so we get this here, and so we get this expression. And by induction, so proving by induction, we could actually get a general formula through this theorem. So suppose f f prime, f to the n minus 1 are continuous on 0 to infinity, and f with the nth derivative is piecewise continuous on 0 to infinity. And suppose all of these derivatives in the function are of exponential order with c such that we have this from the definition of exponential order for all the k. Okay, so for all the derivatives including k equals 0, which is the not, just a function. Then for s is greater than c, we have the Laplace transform of the nth derivative is this formula here, okay? Where fs is just the Laplace transform of that first function. So this is a very important theorem, and just notice what you're seeing here. Okay, we get the Laplace transform of the function, but you're also getting the original function evaluated at t equals 0, okay, where the Laplace transform integrates from. And so this looks like an awesome way to solve initial value problems. It is, okay? So consider the IVP where an does not equal 0, okay? That there has to be definitely not equal to 0. And the AI are constants, okay? And suppose you have this differential equation here. So it's a linear differential equation with constant coefficients where an is not equal to 0. And suppose you have these initial conditions. So y of 0 is y naught, y prime of 0 is y1, and on and on. Then apply the Laplace transform on both sides of the equation. And by linearity, you get this over here. And now what could you do? Well, we have a formula for the nth derivative. So we could plug the nth derivative there. We have a formula for the n minus 1 derivative there, okay? And all the way down to this, which is a naught ys, okay? Because the Laplace transform of yt we call capital Ys. And g of s is the Laplace transform of g of t, okay? So check this out, okay? We have an equation free of derivatives. We have an equation free of derivatives. Yes, this f prime 0, that's just the initial condition, okay? That's just a number from that's fixed from the initial conditions. So the rest is, so this is actually free of derivatives. This is not a differential equation anymore. It's an algebraic equation. It could be written this way, where p of s is equal to this. Q of s is a polynomial in S of degree less than or equal to n minus 1, consisting of products of coefficients of ai and y sub I, the initial conditions. So if you just combine all of these, like, Sn minus 1, y0, and the rest of these into this Qs, that's what that is. And g of s is the transform of g of t. Okay, what's important here is that you're left with a polynomial equation. And so we've transformed the problem from a differential equation problem to an algebraic problem. And so I write here, the Laplace transform may be used to transform a linear differential equation with constant coefficients. That constant coefficients was important because of, how we wrote this formula here. I mean, technically, you can generalize these results, but we're only concerned with constant coefficients. After solving for ys, so you solve this equation algebraically for ys, and don't forget ys is the Laplace transform of what we're what we're solving for, the solution of the differential equation, the original differential equation. So you solve algebraically for ys, and after solving for ys, you then inverse Laplace transform to get y. Okay? So this could be summarized with this diagram here. T-domain is where we generally work with differential equations. In the T-domain you have the dy dt and nth order derivatives there of that. And so, what do you want to do? You want to find this unknown function y of t that satisfies the differential equation and the initial conditions. That's the problem. What you do is you apply the Laplace transform on the differential equation, and you now get this algebraic equation in ys. This is now in the S domain, okay? This is where ys lives instead of yt. Solve for ys algebraically, and then inverse Laplace transform back to y of t, and you get a solution to the IVP. And in fact, the Laplace transform, as we've seen, actually already incorporates the initial conditions, so you need them. So this is how you solve differential equations in a nutshell using Laplace transforms. All right, so let's look at examples of this happening. So use the Laplace transform to solve the IVP that you see here. This is a differential equation, y of 0 equals 6. What do? We apply the Laplace transform to get into S space, all right, S domain. We get this left-hand side and that right-hand side. Plugging in the result for the Laplace transform of the derivative, we got that right there. Okay, and here Ly is just really just a change of symbol there. And this here comes from the Laplace transform of sine 2t. So this is sine 2t Laplace transform. And now you have this algebraic equation. Okay, where'd that 6 come from? Well, that 6 is just plugging in the initial condition y of 0 equals 6. And we have this algebraic equation now, and we solve for ys. Okay, you get that ys is equal to this. And notice that S3 shows up here, and S plus 3 shows up here and here. So you want to combine them. So common denominator, combine them, and you get this. And why do you want to combine them? Because you want to do the partial fraction decomposition. You should combine them and not have same factors there, okay? And then you just do the partial fraction decomposition on the combined term. So let's do that. Okay, s squared plus 4 is a irreducible quadratic, so you can make this assumed formed. And you're welcome to watch the Calc 2 video on partial fraction decomposition to see why we've chosen that. But anyway, if you do that and you solve for a, b, and c, as we've done in the partial fraction decomposition, you'll get a is equal to 8, b is equal to negative 2, and c equals 6. And so that means that this could be written this way. And so, okay, we solved algebraically for ys. And you know, and technically solving algebraically for ys was just, you know, getting this. But we do the partial fraction decomposition because we know we're about to inverse Laplace transform. Okay, and it's easy, you know, it's easier to do the inverse Laplace transform on the decomposed fraction. Okay. So the inverse Laplace transform of this bilinearity is equal to this over here. Okay, bilinearity. So you just break up these sums, and you get the what's inside the inverse Laplace transform in the forms that we have a table for. Okay, and you inverse Laplace transform, and you get this. And look at that. We don't have these arbitrary C1, C2, or whatever, because the initial conditions are already incorporated into the Laplace transform. That was a first order differential equation. Let's look at a second order differential equation. Now we have two initial conditions. We apply the Laplace transform on both sides. Here's the left-hand side, and here's the right-hand side. This gives us this left-hand side and this right-hand side by Laplace transform of e to the minus 4t. What do? We now solve for ys, okay? And this is what we get when we combine all the terms. Now we do the inverse Laplace transform to get y of t, the actual solution we're looking for. But of course, we're going to have to do partial fraction decomposition there. You do that, and you would get this, which we've actually done in a previous problem here, okay? And so you'll get this expression there, okay, when you do the inverse Laplace transform. And that's how it works. That's our solution, okay? So start with a differential equation with initial conditions, Laplace transform the equation, solve for ys algebraically, then inverse Laplace transform ys to get yt. Just a quick note on just some of the language around dynamical systems. So we saw this equation that we had when we did the Laplace transform of an arbitrary nth order linear differential equation with constant coefficients. So ys then could be solved for in terms of this right here. A 1 over ps, okay, is called the transfer function. And this is used in the context of dynamical systems. So you have ys is equal to the transfer function times qs and ws times g of s. And this is ys, and we want y of t, so we inverse Laplace transform. And you get two terms, okay? This term is sometimes denoted y naught of t, and this term is sometimes denoted y1 of t. So if you have input g of t equal to 0, okay, so the non-homogeneous part, the input in the context of dynamical systems is 0, then the solution is just y naught, okay? And this would be 0, and so the solution here would be this. And such a solution, this y naught, where you're just taking the inverse Laplace transform of this term, this is called the zero input response. If on the other hand you start with the initial state being the 0 state, which is just all initial conditions as 0, so that qs equals 0, then this here is the solution, okay? Because the y naught would be 0, okay? In this context, this would be 0 because qs is 0. And this is called the 0 state response, okay? So this here, in this case, gives you the 0 input response. This case here, where the initial conditions are 0, is called the 0 state response. And so this just shows you that the Laplace transform can help us decouple those two aspects, input and initial conditions, okay? So that's just important, in particular when discussing dynamical systems.